So in this module, we are going to talk about feature scaling. Let me give you a brief idea about what all we are going to cover. So first of all, we'll start with what is feature scaling. Then we'll talk about why we should perform feature scaling. Then we move on to choosing appropriate feature scaling amongst the multiple choices that are available with us. While talking about this, we'll also emphasize on the common mistakes that people make while making a choice of feature scaling. Then we move on to discuss the advantages and disadvantages of feature scaling. And finally, we'll perform hands-on feature scaling, applying all the appropriate techniques that we learned theoretically on our dataset. Let's get started. So let's talk about what is multicollinearity. In terms of definition, it says when two or more independent variables in our data are strongly correlated, it is termed as multicollinearity. Now, what are independent variables and what is a dependent variable? Let's understand that. So let's say we have to predict the price of a house. That's a dependent variable. We are trying to predict the price. Now, what all factors lead to a certain price? It could be the locality of the house. It could be the property area. It could be the number of bedrooms. It could be how old the property is. So you can think of multiple factors which lead to an outcome. These factors are called independent variables, and the outcome that you're predicting is called a dependent variable. So we are saying when two or more independent variables are correlated, we have multicollinearity. In order to understand this better, we'll have to get a little bit of intuition about linear regression. So in case of linear regression, we have these points, these circles that you see here are the actual data points. And this line that you see here is essentially trying to represent these points. It's a generalization of these points. That's what linear regression does. So let's say in this case, you're talking about one dependent variable, that's some target that you're predicting, using one independent feature, which is x. So in such cases, we used to come up with an equation like this. Now, this is a simple equation of a line. Y hat, or the predicted value, is equal to beta naught plus beta 1 x. This beta naught is called the intercept, and this beta 1 is called the coefficient. Now, you can see that this line is only trying to represent these points. It is not necessarily passing through all these points. So what you have is something that's known as the error. So you have difference between an actual point, which are these red circles, and a point on the line. So for a given value of x here, you have an actual observation, which is this circle. But this is not what you're predicting. What you're predicting would be a point on this line. So the difference between an actual point and a prediction is something that's known as the error. So in general, we will call it error or residual. This is the difference between the ith point's actual value, or the y value, which is the circle, minus yi hat, which is the point on the line. Now, regression line is found keeping in mind that we want to minimize such errors. Now, errors could be positive or negative, so we try to minimize not just the difference, but the squared error. This is the objective we keep in mind to determine that line. And in case you have multiple variables, you would be extending this equation to this form. So you would be writing something like a beta naught plus beta 1 x1 plus beta 2 x2. What are these beta 1s and beta 2s? These are the coefficients of different independent variables. x1, x2, x3 up to xn are all different independent variables. Why are we talking about this? Because we need to understand what role do the independent variables play when it comes to regression. And only then we'll be able to appreciate why we need to treat multicollinearity. So we are fine if the target and the independent variables are correlated. But what we don't want is this scenario, when the independent variables, let's say in this case x1 and x2, are themselves correlated. And that is when we have multicollinearity. So we don't want to eventually come up with an equation which finds a relationship between x2 and x1. The objective of the problem was that we wanted to predict, let's say, the price of the house using the area occupied by the property. But if you try to explain the area occupied by the property with the help of number of bedrooms, that was not the objective. These could be two different variables. Next, we'll be talking about why we need to treat multicollinearity. Now let's understand why to perform multicollinearity treatment and how does it really affect the outcomes. So we know this is a general linear representation of the independent variables against the target column, a multiple linear regression equation. Let's say we only choose two features and try to explain a y. So let's say we choose x1 and x2, and these are the actual coefficients, and this is the intercept. So y hat is equal to 10 plus 2 times x1 plus 5 times x2. But in addition, if x1 and x2 also have a linear relationship, you'll have another equation, which is something like this. Let's say x1 is equal to 2 times x2 plus 1. So we expected a linear relationship between y hat and x1, x2, but we also see a linear relationship between x1 and x2. Now, using this value of x1 from this equation, if we put x1 is equal to 2x2 plus 1 in this equation, what are we going to get? So this is 10 plus 2 times, and we put this entire value here. And if we simplify it further, multiplying the values within the parentheses, we get 4x2 plus 2 plus 5x2. Again, adding the constants like 10 plus 2 and this 4x2 plus 5x2, we get something like this. So in this equation, if you see, we do not have x1. Can we say it can be written as 0 times x1? So we can write 12 plus 0 times x1 plus 9x2, something like this. This is another equation. This was the original equation. Is this equation wrong? Not really. Given the fact that x1 and x2 have a correlation and they are linearly associated, we derive this equation. Now the confusion is 10 the constant or 12 the constant? Is the coefficient of x1 2 or it's 0? Is the coefficient of x2 5 or it is 9? That's where there is a confusion. And this confusion would further increase if we now try to put x2 here in terms of x1. Let's say we go back to the original state where we started, and this time we write x2 is equal to x1 minus 1 divided by 2. You can do this arrangement, take this to the left-hand side and divide it by 2. So this is what it is. And now we're going to put x2 as x1 minus 1 by 2 in this equation. Now what will happen? Let's put this value. So 5 by 2 times x1 minus 1. 5 by 2 is nothing but 2.5. So we can simplify that like this. 10 plus 2x1 plus 2.5x1 minus 2.5. And if we simplify this further, we get 7.5 plus 4.5x1. 2x1 plus 2.5x1 is 4.5. 10 minus 2.5 is 7.5. Can we bring another 0 times x2 here? Yes, we can do that. And this is our new equation. So this is another equation. This was the original equation. Should the intercept be 10 or 7.5? Should the coefficient of x1 be 2 or 4.5? Should the coefficient of x2 be 5 or 0? So this is where there is confusion. Let's summarize. This is where we started, and we got 2 more equations like these. Now the point is that your model is really confused. The model doesn't know what are the right coefficients to rely on. And all of this is happening thanks to the correlation between x1 and x2. So if you see, all the coefficients are varying now. The intercept here is varying between 7.5 to 12. The coefficient of x1 is varying between 0 to 4.5. And the coefficient of x2 is varying between 0 to 9. So the coefficients no longer are reliable. And as a result of this, we are not able to finalize the right equation. Again, why? Because we have multicollinearity in this case. So to sum it up, due to multicollinearity, the model coefficients begin to vary more. And as a result, the model becomes unstable. This is the reason we need to perform multicollinearity. Now, coming to multicollinearity treatment, there are certain popular choices. First is, if we have a correlated pair, we can drop one of the features. So let's say we have some data where there are limited pairs of correlations. If there are features found to be correlated, we can keep one feature and drop the other. That's one option. The second option is VIF, or variance inflation factor. It's a very powerful technique to deal with multicollinearity, and it's more sophisticated than the first approach. So we continue to drop the features with high VIF value. We'll discuss this concept at length. Third would be we can transform the data using techniques like PCA, principal component analysis. The last one is that we can apply ridge or lasso regression. So all these techniques are valid and can be used depending on the appropriate scenario. We'll also discuss which is the most appropriate amongst these techniques. Now coming to the common mistakes to be avoided, let's understand what are the possible mistakes that might occur. Going through these 4 techniques, so the first approach talks about keeping one of the correlated features and dropping the other. This might be feasible if you have very limited features which are correlated, like 7-8 features. But if you have too many features which are correlated, it might not be a practical technique to work with. Coming to the third technique here, which is transform the data using PCA. Now that's a great technique. Unfortunately, PCA itself, principal component analysis itself, is a complex process, and it's not understood by people practicing business. So you'll struggle to explain the outcomes of PCA to the business representation. That's one challenge. It's a great technique, very powerful, and does its job quite well, but it's complex and not so easy to understand. The last technique which we mentioned is applying ridge or lasso regression. Now, ridge and lasso are not intended to treat only multicollinearity. These are regularization techniques. So, ridge and lasso would help you reduce multicollinearity by accordingly deciding the coefficients of the correlated features, but it is not going to treat it completely. So now we are left with one choice, which is variance inflation factor. And that's what we're going to discuss next. What is variance inflation factor? To begin with, let's go back to our multiple linear regression equation, which we've already seen a couple of times. Now we know in order to evaluate a linear regression model, we use something called as R square, or the coefficient of determination. This was used to assess how good the model is. And the interpretation of coefficient of determination is something like this. So let's say if we get an R square value of 90%, it means that 90% of the variability in y hat, or the predicted values of target, is captured by the independent variables that we've used in the model. It means we have a good model. The higher the value, the better it is, and this value always ranges between 0 to 1. 1 means 100%. Just a small twist here. If instead of predicting the value of y, we begin to predict the value of each independent feature. For example, we try to explain x1, which is an independent feature, with the help of other independent features like x2, x3, and these are the coefficients here. Likewise, if we try to explain x2 with the help of other independent features from x1, x3 to xn, this is another linear equation. And likewise, for x3, we can have a linear equation. We've not added the constants here because that's not important, just trying to explain the core idea. Now, from regression, you know, for each of these equations, you can find out an R square value. So, in VIF, we fit a linear regression model for every independent variable using all other independent variables as predictors. Now you can imagine for each of these linear equations, we can always find an R square value. Let's say the first equation has an R square value for the prediction of x1. The second equation has an R square value for the prediction of x2, so on and so forth. Once we get these R square values, we can easily get the VIF. What is the relationship between this R square and VIF? So it goes like this. VIF for a variable xi, it could be 1, 2, 3 up to n. For a given variable I in general, VIF is given by 1 over 1 minus this R square value of that ith feature. For x1, the VIF would be 1 over 1 minus R square for this equation. So let's understand this VIF a little better. How is it related to this R square? So if this is our VIF equation, as we saw on the previous slide, if R square goes up, then 1 minus R square would go down. And as a result, this entire expression, which is numerator divided by denominator, because the denominator is going down, this ratio is going to go up. So in general, we can say as the R square value increases, the VIF also increases, because this R square increased, the denominator went down, and the overall ratio went up. To give you an example, if R square value is 0.8, you can try putting 0.8 here. You'll get 1 minus 0.8, which is 0.2. And 0.2 would give you VIF of 5. 1 over 0.2 is 5. Likewise, if R square value was 0.9, which is a greater value compared to the previous value, you can see 1 minus 0.9 will give you 0.1. And 1 over 0.1 is going to give you VIF of 10. So as we increase the R square value, the VIF also increases. An extreme case could be that your R square value is 100% or 1. And if you do 1 over 1 minus 1, 1 minus 1 is going to be 0, then VIF tends to infinity. Now, an important point to note with respect to VIF is that VIF-based feature elimination is always done recursively. That is one at a time, until we reach a stage where no variable has VIF greater than a threshold. So generally, we will be eliminating features which have a VIF value greater than a threshold, but we don't eliminate them all at once. We do it recursively, one variable at a time. Why? Because when you drop features, the VIF computation would be revisited, and as a result, the VIF values vary. So now it's time for us to move on to the hands-on exercise, where I'll show you some of these techniques in action. All right, so we are at the Google Collaboratory one more time, and I've already pointed to the data source, which is a very popular Wisconsin cancer data set that's available at UCI Machine Learning Repository, a very popular source for data sets which have been used for research purposes. So I'll provide you a link for that as well. You can always access that data set. Now, let's start working on the data. So we begin by calling the basic libraries, NumPy, Pandas, Matplotlib, and Seaborn, and this is where we are. These libraries have been imported. We begin by reading the specific data set using the pandas read CSV method, and we are storing it by the name of df, in short for data frame. We can check how big this data is. We can always do df.shape, which tells us rows and columns. So we seem to have 569 rows and 32 columns. Essentially, the features in this data set are the outcome of a specific test for cancer, which is known as the FNAC test, fine needle aspiration test. Let's check the first few observations of the data set to get a better idea about how the variables are. So it doesn't give the names of the variables, but if you check the source, that is the UCI repository, it has the proper names of each of these variables. So right now it shows the variables are from V1 to V32. Like I said, since we have the names of the actual features available, and this is the mapping of the features, so we've created a dictionary where this is the key and this is the value. These are the actual features available on that page. And we are using a rename method on the pandas data frame to apply this mapping. What is this mapping? This mapping is in the form of a key value pair or a dictionary format. And we are applying this in place, which means these changes will be effective on the data frame. So let's do that. This will make the variables more relatable and might give a little more meaning to the variables, though we don't become a domain expert by just doing that. But let's try to check the head again after renaming the features. So one thing you see clearly is that first feature we would have otherwise understood as some number which has a meaning is just a patient ID. And the second feature here is the diagnosis. Now this is the dependent feature. So originally this data was used to predict the cancer, whether the outcome of the test was malignant, which is confirming a cancer, or benign. And using these features here, we were supposed to predict the diagnosis. But for our exercise right now, we are only going to concentrate on the multicollinearity. We are not predicting the outcome. So we will drop the features like ID and diagnosis. We don't need these. ID is as such a nominal variable, doesn't have to do with cancer as such. And diagnosis is not our focus because we are trying to eliminate the correlations between the independent features. So we are dropping these two features in place using df.drop. Now we're talking about two approaches. First is that we can remove one correlated feature from each correlated pair. Before we do that, let's just look at what's the state of current correlations in the data. So we can do this using a heat map. We've just adjusted a figure size and we can try multiple sizes, whatever works best, we can go for that. And using a heat map to which we are passing a correlation matrix, df.cor. That's the way to call it. And we are choosing a color map, which essentially is going to show us the shades of reds and blues. We have mentioned that the range of correlations would be anywhere between -1 to 1. If you know correlations, you know this is a value which always ranges between -1 to 1. Let's visualize this. So we started with 32 features. We have dropped 2 features. Right now, we are looking at 30 features. Now, if you're looking at 7, 8 features, you can always do something that's known as the annotation here, and you will be able to read the values of the correlations itself. But when you have too many features, it may be a lot of clutter to print the values on top of this heat map. So what we're doing instead is we are trying to figure out how many correlated features are there. Because even if we start manually counting and if the values were here, there's a high likelihood that we make a mistake in counting. These are not limited features. These are decent amount of features. So we will be writing a function finding out the correlations which are greater than a threshold. So we're writing a function which is known as correlated feature pairs. You can give any name. This is our choice, which takes an input as the data set and a threshold that you want to check for. We are creating an empty list, which will be storing some correlated pairs after some time. And we are generating the correlation matrix on the data set, which has been passed as an input. We are applying the correlation matrix. Now, we are iterating over this correlation matrix using 2 loops. First is a loop that's going to go over all the columns starting from the index 0 to the last column in the data. And the second for loop here, which is a nested for loop, is going to go over all the values starting from 0 up to the ith value here. Finally, we will be looking at the absolute value of the correlations at the index I, j, which is greater than threshold. If we find it, we will store it for feature 1 as column I, for feature 2 as column j from the same correlation matrix. So we will get to know which is the feature 1 and which is the feature 2. And finally, we append it to the list of correlated pairs in the form of a tuple. So feature 1 and feature 2 pair would be an element of this list. And we are returning the correlated pairs. This is where we have set a correlation threshold, let's say 0.9. And at this point, we are applying this function that we just discussed, which seeks 2 inputs, the data frame, which is our actual data frame that we read, and the correlation threshold, which we just decided here as 0.9. We can always change this and look at different correlation outcomes. What we are checking after that is we are printing an outcome which is going to suggest how many correlated pairs were found. So this is a string. It will say total and whatever will be the length of the correlated pairs. Correlated pairs is basically a list. So the length of the list will tell you how many elements are there. And what are the elements of that list? Just the correlated pairs. So it's going to count the total number of correlated pairs that it finds. Then we are getting inside the correlated pairs and printing those pairs like this. So it will say feature 1 and feature 2. Let me run this. And then you can appreciate the output. So it says 21 correlated features found. And which are these correlated features? These are the names of the correlated features. These are 21 pairs that it has found. Now let's say you decide that of all these correlated pairs, you simply want to drop the first feature. We discussed that as the first approach, that if you have correlated pairs, you can keep one feature and drop the other. So for that, we are again writing a similar function, but it has a little different usage. So we are writing another function which is called correlation detection. Again, the name is not important. It's a user-defined name, which takes the input as the dataset and threshold like the previous function. But for the features, we are using a set form. Why? If you see this outcome here, you'll see a lot of first variable names repeated. For example, area worst, if you see, this is something that appears 5 times. Perimeter worst, this appears 4 times. When you create a set, it will always store the unique entries. That's about the basic data structures in Python. List can store repeated entries, but set would only store unique entries. We want to be eliminating these features, so we would need their unique names. Again, we are creating an empty list called correlated pairs. We are calculating the correlations and storing them as correlation matrix. 2 for loops like the previous stage. Exactly the same approach. We are looking at absolute values of correlation which exceed the threshold, and we can set this threshold once again to 0.9. From the correlation matrix, we are taking the name of the feature which is found to be correlated, the first feature, and then we are adding it to our set. So notice for the list, we used append method. For a set, we are using the add method. This would return a set which will have unique entries of those features which have been found in correlated pairs. So we have taken the first feature of the 2 paired features which are correlated. Let me run this. This is just a function definition. Now to apply this, we are first making a copy of the data frame because we don't want to change the actual data. We are making a copy of the data frame, which is called df1, a copy of the original df. And here we are applying that function. Which function? The function that we just discussed here, which takes the input as the data frame and the threshold, which we have passed as 0.9. And now we are checking how many features are there in the set, which we are going to eliminate. So it says 10 features. Can we count this here? So this is 1, this is 2, this is repeated, so we'll not count it again. 3, 4, 5, again repeated, will not count. 6, 7, 8, will not count the rest. 9, and 10. So there are 10 features that we saw here, which we have detected. You may be wondering, we could have easily counted it here. This may be easier for now, but what if you're dealing with 150 features? You'll not be counting it manually, right? So it's better to write functions which would do your job accurately. Now let's check what are these correlated features. So these are the same 10 features that we just counted above. And now it's simple. We just have to do another df1.drop. Just pass the set. 2axis is equal to 1. It simply means that we are dropping these columns. Which columns? Columns represented by this set. And in place is equal to true. So now let me scroll up and check the shape of the data frame again. Shape 1 means columns. So we are left with 20 columns now. So we started with 32 columns, dropped the ID and the diagnosis, left with 30 features. Of the 30 numerical features, independent features, we have dropped 10 features. We are left with 20 features. If we now check the correlation matrix again through the heat map, let's see how does it look like. So it again may not be very clear, and a couple of places you may feel that there are still some strong correlations. And we are not annotating here to read these. But can we apply the same function that we wrote earlier, which actually detects the correlated pairs, and see if in this data frame, df1, now we have any pair which is correlated. We are writing the same function, takes the input as the data frame and the correlation threshold, and we are printing if we still have any such pair. And what does it say? Total 0 correlated pairs found, which means we have eliminated all the features which have correlations values greater than 0.9. Now let's move to the second approach, which is VIF. Now VIF as a concept has already been explained as a part of theory, but here we'll be directly using VIF through a library called stats model. Let's make a copy of the data frame because this is a different treatment. So we need to make another copy of the original data frame. And from the stats model, stats outliers influence, we are calling the class called variance inflation factor. Here, we are trying to create a nice data frame, which is an empty data frame. It has one column which stores the feature names of the original data that we copied, and another column which will store the VIF values. Now, VIF is something for which we don't have to write a function. We will just use the existing function that's available through this class. So what we are saying is that for each I in the range of the data frame columns, df2.columns basically means all the features which are present in the data frame 2, which is a copy of the original data. So we are going over each feature, and to the VIF or variance inflation factor, we are passing the values within the data frame along with the column name. And this is the only input that this function, which is a ready-to-use function, needs. Finally, it will give us a data frame which will have 2 columns, name of the feature and its VIF value. And we are printing VIF values, sorting it by VIF in a descending way. Ascending is equal to false means in a descending way. So we'll get to know which feature has the highest VIF value. Let's run this to see VIF values are really alarming here. And these are starting from 63,000 something to 24. So that way, if you see, for all these 30 features, the VIF values are much greater than 5 or 10, which is a typical threshold. Based on VIF, we drop the features one at a time. So we will be dropping the one with the highest VIF value first, and we have to do it recursively. It's a common mistake. A lot of times people would detect VIF and they'll drop all the values which are greater than 5 or 10 or the chosen threshold at once. That's not how it is supposed to be. When you drop one VIF value, the highest VIF value, the entire VIF calculation is revisited. So a lot of changes will happen here. This way, if you see, if we drop all, we'll not be left with any feature. Then there's no point doing VIF, right? So we'll do VIF in a proper way. For that, here is a small piece of code. We have chosen the threshold for VIF as 10, which means we are trying to eliminate those features, which when explained by other independent features, have an R square of 90% or more. So we have set a flag here, which is set to true. Why have we done this? We are going to eliminate the features one at a time, and we don't know how many times we are going to run it. So in such cases, you will not use a for loop. For loop is a loop which goes from one end to the other end. In cases where you don't know how many exact iterations you need, you will be using a while loop till you reach a point where there is no feature with a VIF greater than 10. So you want to terminate this loop at that stage. So we are setting the while loop to begin with as true. We are creating the same data frame that we talked about. We are putting it through a loop now. The same thing that we discussed a couple of lines above. We are putting this just through a loop. So in this particular case, we are checking for every feature whether its VIF value is greater than max VIF. What is max VIF? This is our threshold here that we have set. If the VIF value of the feature is greater than the max VIF, we are dropping that specific feature. Access is equal to 1 refers to the column. And then we are also printing a message which says remove variable with high VIF. We are mentioning the name of the variable and also the VIF value that this feature had. But if the feature does not have a VIF greater than the maximum value permissible or threshold, we are setting the remove flag to false. Now, the moment this is set to false, this while loop will stop execution, which means you've reached a stage where no feature has a VIF greater than threshold. So let's run this. And now, after executing this, let's just try to read the message. There are many features which seem to have been dropped. And every time, because we're printing the message, it continues to drop them iteratively. But has it dropped all the features, all the original features? Of course not. We'll have to check. It has only dropped the features which have a VIF greater than the threshold. And if you see, the VIF values seem to be recomputed. In our original output, if you see, the lowest VIF value was 24. But if you can see here, we've dropped features with VIF up to 11.17. Where would this have come from? This would have come because the VIF values were recomputed. Let's check what's the shape of the data frame now. So now you see you're left with only 7 features. We started with 32 features, dropped the ID and diagnosis column. Those were not required. We were left with 30 features when we started VIF. And out of 30, 23 features have been dropped. So this is a very powerful technique which has eliminated 23 features out of 30. And now if we try to look at the heat map, because we're left with only 7 columns, we can also afford to do the annotation with 2 decimal places display. Let's see how our heat map looks like. Here is the heat map. So now if you see, there is no pair of correlations which is to the north of 0.9 or even close. All the features that we have do not seem to have correlations. By the way, correlation matrix is always symmetric. So if we read the value, the lower triangle or the upper triangle, that's one and the same. We don't have anything which is significant here. So VIF has done its job pretty well. In case we want to check if there's anything that's still left and using the earlier function, the first function we defined here, this time passing the input as data frame 2 and the correlation threshold, which is 0.9, it'll again say 0 correlated pairs found.